Well, good morning and welcome to webmix's webinar, The Chemistry of Printing Resins, What Makes Them Great. My name is Bernie Jaroslaw. I'm the marketing manager here at webmix, and I will be facilitating this morning's webinar. I want to begin with a couple housekeeping items. First, in the upper right-hand corner of your screen, you should see a questions box. So you're certainly able to ask any questions you'd like, but please type them in throughout the presentation, and then Cory will answer them at the end. And also, if you're a CDT, this webinar is approved for 1 hour of CE credit toward your certification. You'll receive an email within 1 to 2 days that will tell you exactly how to obtain the credit. There will be a simple test involved, so listen carefully, and then we take care of that credit for you. Lastly, this webinar is being recorded, so within about 24 to 48 hours, it will be up on the webmix website in the webinar section, so you're able to review it any time after. Well, this morning, I have the pleasure of introducing Cory Lambertson. Cory is a technical services rep here at webmix. As a certified 3-shape, Roland, and a SIGA trainer, he develops and conducts CAD/CAM equipment and software training and provides technical support and assistance for our digital customers. Before joining webmix, he worked for 2 years in his father's dental laboratory, Heartland Dental Lab in Hillsdale, Michigan, as a 3-shape CAD/CAM technician. Cory received his Bachelor of Science in Finance from Andrews University in Berrien Springs, Michigan. Again, today, Cory will be speaking on the chemistry of print resins, what makes them great. So, Cory, if you're ready, let's talk about resins.
Thank you, Bernie. I appreciate that well introduction, as always. So let's go ahead and begin. We are going to cover today the chemistry of print resins and what makes them great. So of course this is for 3D printers, and the type of technology of 3D printer that you'll need is a stereolithography style 3D printer. So stereolithography, I just want to define what it is a form of 3D printing technology used for creating models, prototypes, patterns, and production parts in a layer-by-layer fashion using photopolymerization, a process by which light causes a chain of molecules to link, forming polymers. So I'll make sure everybody can see this real quick.
It is only seeing the intro screen.
Go to show screen. Click there. There we go. Oh, all right.
Sorry about that.
All right. So the first slide was just the title of the presentation, and the second slide was the definition of stereolithography. So let's take a look at those style of printers that use this 3D print resin, this photopolymer resin. So the types that we have is we have a laser stereolithography, which uses a laser to cure the resin. We have DLP stereolithography, which uses a projector, which is the most popular in dentistry currently. And then we have mask stereolithography, which uses a LCD mask to block light from shining through and allows light to shine through to cure that layer of resin. So these type of printers, these three here, these are all forms of stereolithography. And so the resin that you're going to use for these types of printers is what we're actually going to cover today. So resin chemistry, what is actually in the resin itself? So we have monomers, which helps play a role in the viscosity. A higher viscosity resin is going to be thicker. A lower viscosity resin is going to be a little bit runnier, more like a water-like consistency. We also have a catalyst, which is the photoinitiator. This is a light-sensitive material that generates radicals to solidify the monomer. And then we have pigments or UV blockers, which adds color and controls light penetration. This helps alter the speed of the reaction. So there's three main parts that are three main roles in each resin formula. So that's a monomer, a catalyst, and then a pigment of some sort, or UV blockers. There are two different types of photopolymer resins used in 3D printers. There's a methacrylate base and an acrylate base. So the differences are significant. A methacrylate base is what we're going to see in the dental industry. The acrylate base resin we'll see more in the hobbyist resins and also in the lower quality resins that are advertised as dental resins. Methacrylate based resin, it has a low reactivity, it's low shrinkage, and has a stable cure speed. It is low in the toxicity scales, and it's suitable for medical devices. For example, a light cure resin that is commonly used at your dental office would be used for fillings. That's a methacrylate based resin. And the raw materials are limited. So this is why the methacrylate based resins tend to be a little bit more expensive than the acrylate base. The acrylate base, they have a higher reactivity, high shrinkage, unstable cure speeds. You'll see these for the hobbyist resins, like Fun To Do resin. They have a lot of hobby resins, and so they're going to be more of an acrylate base than a methacrylate. And also the acrylate has a higher toxicity. So you're not going to see biocompatible resins with an acrylate base versus methacrylate. You will see a biocompatible resin. So let's take just a little bit deeper look on how the photopolymerization process actually works. So this is the reaction between light and a liquid that's going to form it to become a solid. So we're going to start with a light source. And so there's two main light sources in 3D printing currently. There's the 385 nanometer, which is you'll see that in the higher quality 3D printers. And then there's the 405 nanometer light spectrum. So we're going to cover that in a moment. But that light source is going to shine onto the liquid resin, which is going to activate the photoinitiator. It's going to create free radicals into the liquid resin. And so the radicals are actually spread out in a liquid state, and when it actually starts to solidify, they become closer and closer together, which is what makes that liquid resin into a solid. So liquid resin is then going to form into a plastic solid object, which is completing the polymer chain. So this is just to solidify each layer. This is going to happen for every single layer as the light is exposed, and so this is what's going to create a solid object. So like, for instance, our models, our surgical guides, this is actually what's happening for every single layer. Really cool process, really cool to see under a microscope. But beyond curing your object, you also need to have a surface cure protocol for your resins, especially if it's going to be a biocompatible resin. So need for surface cure post-curing. So this is after you clean your object that was 3D printed, and it was you're going to clean it in an alcohol bath. You need to do a post-cure process, especially if it's biocompatible. What happens is that oxygen inhibition is on the exterior surface, results in unreacted radicals in the monomers at the surface. So technically the object is still toxic at this point until you put it through some sort of post-curing process. Now each resin itself is going to be unique on what its post-processing or post-curing requirements are. So just a tip, read the instructions of use for every single resin that you use, just so you actually are following their guidelines on how they actually achieved a biocompatible device. But some factors that actually play a role in this is we have the wavelength of the post-curing unit. The wavelength, if it's a lower spectrum on the scale, so let's say if it's below 385, let's say it's down in the 200 nanometers, it's actually that's a stronger, more intense light. And so with that, you're actually going to have you can actually complete a surface cure just from having a very high wavelength cure unit. Also the power density, how much actual light is being shined or being used when curing. So that's rated in milliwatts per centimeter squared. Some of these actually may seem a little confusing at this point, but just bear with me. So if you have a curing unit that has a high powerful light, a very bright light, it can actually complete that surface cure. Oxygen concentration, we'll see some curing units out there that have a nitrogen air barrier, so they try to deplete out the amount of oxygen before it exposes it to light to complete that surface cure. the amount of time, you'll see some resins require a curing cycle of upwards of 20 minutes or a half hour. What that is doing is that's giving it the amount of time for a certain curing unit to actually complete that surface cure. Also, the resin chemistry itself, we can change the formula so that we can reduce the amount of oxygen inhibition that is happening on the external surface, and also temperature. We can apply temperature to help complete that surface cure. So we'll see curing units that apply multiples of these rules on the right hand side. So for example, the Form Cure from Form Labs that has heat and a high spectrum light to complete the surface cure, which is what is needed for their surgical guide resin. For example, our Variguide resin, it currently needs a low oxygen concentration and a high power of light and high power wavelength to be able to complete the surface cure. So that's why we actually sell the NK Optics curing unit. And so there's multiple forms for creating this final surface cure and completing the surface cure. But most importantly, remember to read through the instructions of use for post curing. Whatever resin you have purchased, it's crucial that you follow that. So let's cover the differences in wavelength between 385 nanometers and 405 nanometers. So right off the bat, you must use a resin formula that is compatible with the printer's wavelength. So if you have a 385 nanometer resin, you cannot use that in a 405 nanometer printer without having some sort of issue or accuracy issue. So if I was to use a 385 nanometer resin in a 405 nanometer spectrum printer, you'll actually have resin that is cured in areas that you didn't want it to, because the light penetration is actually higher in the 405 nanometer. So just a tip, read the instructions of use for any resin. I can't stress that enough. It is crucial that you read that. The 385 nanometer light is an ultraviolet light, is higher energy. So because it has such a higher energy, you can actually control the light penetration into the layer or into the object that we're curing. It's going to be more of a surface cure and not so much as a higher depth of cure. So we can actually get a higher accurate object out of a 385 nanometer spectrum printer than you can out of a 405, because we have that controllable penetration. Also, with a 385 nanometer light spectrum, you can actually print a clear resin and have it remain clear. It prevents the yellowing of clear resins, that light spectrum. The 405 is a visible light. It is a lower energy, but because it is a lower energy light, you can't actually control that light penetration, the depth of cure. So I'll see a lot I follow different dental printer Facebook groups, and I always get a kick out of people that are using a 385 resin and a 405 printer, and they can never have, or they'll never have an accurate object, or they'll say, oh, look, it cured into the supports. I was printing a surgical guide, and now my object is cured beyond the supports, and it looks more like a blob. And the reason why is because they're using a 405 light and a 385 resin. Also, with the 405 nanometer resins, they're going to have to place pigments in it to prevent it from the depth of cure being too far. So you'll never actually receive a true clear resin with a 405 nanometer printer. And if you do try to print a clear resin, you have a high chance of it actually yellowing immediately after printing. So besides having two different spectrums of printers and two resins that have to fit those different spectrums between 385 and 405, we also have two different types of resin that are designed for two different styles of stereolithography printers. So with a DLP 3D printer, you have to design a resin that has a fast reaction speed, because the intensity of the light of the projector is actually going to be fairly low. So in that milliwatts, that light density, that milliwatts per centimeter squared, we're going to see a range between 4 milliwatts to 15 or 20 milliwatts per centimeter squared, depending on what printer it is and the manufacturer, but it's going to have a lower intensity of light So to be able to have an appropriate resin and not have a resin that takes forever to cure, you're going to develop a formula that has a faster reaction for DLP style printing. Also under this DLP style printing, the mask SLA, mask stereolithography style resins, those are also going to need a fast reaction. So you're going to see DLP resin and mask SLA resin, those are going to be almost identical. The laser stereolithography, which is similar to like the Formlabs printer, those actually have you're going to need a slow reaction, because those resins, or the printer itself, has a very strong light source. It's actually at 250 milliwatts per centimeter squared, which is extremely powerful. And if you had a fast reaction, you can have some major side effects of creating like flash in the on the cured object itself. So you need to have a slowed reaction, a slow cure time for stereolithography laser resins. So this, how I can tell what resin I'm actually using for my printer. If I have a DLP printer, make sure the resin that you're purchasing states it's for DLP technology. It's going to state it on the external label of the bottle, and also it's going to state that in the instructions of use. Once again, read those instructions. You will have great success if you read the instructions of use and follow the guidelines. So when we manufacture a resin itself, as webmix itself, we manufacture resin and for 3D printers. And so when we actually develop a formula, there's a lot that goes into the actual production of it and making sure that it's a quality resin. And so how do we qualify a new formula? Well, the easy answer is we print a lot. On average, our R&D department spends over 200 hours of printing just on one formula. And if we have to go and change the formula, well, that whole process starts all over again. So just some key points that actually makes that we look for in a quality resin, that we make sure that we've passed these guidelines. One of the options, or one of the keys, is that we make sure that we have a smooth viscosity for 3D printing. So we don't want something that's really thick like honey, or we don't want something that's really runny like water when creating a resin for 3D printing. We need it to have a smooth consistency, a smooth viscosity. It's around 700 to 1,000 centipoise is what we are shooting for. After we dial in the viscosity of the resin, we're going to look at the surface quality of the prints and the tackiness. Does the model itself or the object itself that we just printed, is it extremely tacky? If it is tacky, how do we post-cure it? Do we need to create some sort of oxygen inhibition layer around it? Does it need to be in a glycerin bath, or does it need to be in a nitrogen dead zone? So we're going to go into that qualification as well, make sure that it has a high surface quality and it's easy to post-process and easy to cure. We also want to make sure that the shrinkage is low, and if there is any sort of shrinkage value to it, we run through about 20 different prints just to calculate what the shrinkage value is and provide that to the customers. So we want to make sure that the resin itself has a low shrinkage value, and beyond low shrinkage, we don't want it to warp. We want it to stay, have a stable surface to it. We don't want it to start to warp up around the edges or change dimensionally after it's being printed. So we have to change our formula to make sure that we have low warpage and low shrinkage. Also, we want to make sure that it's easy on the customer, has low skin irritation. We don't want to provide a resin to our customers that is extremely toxic. We want them to be able to use it with ease. Suspended pigments. When we create a resin that has any sort of coloring in it, we put a pigment suspender in it to make sure that the coloring stays in a homogeneous mixture. We don't want it to settle out within a couple hours of printing. If anybody on this that's listening to this webinar today, if you already have a 3D printer, you'll notice over time the pigments or the coloring in it starts to settle out, and you have to mix that resin before you start printing. Some resins, some manufacturers, they are guilty of not putting any sort of pigment suspender in it, and so what happens is the pigments settle out and you have to mix quite a bit. You don't want to spend your valuable time mixing your resin. You want to be printing your resin. So we actually put a pigment suspender inside of our resin formulas. We also do flexural strength and compressive strength. We need to make sure that it's going to meet our customers' needs and requirements for whatever material we're trying to manufacture. This was an issue, or not an issue, but a concern when we create our model material. We needed to make sure that it replicates a stone-like compressive strength and stone-like flexural strength for our customers. We also want to have low odor. This goes back to the being toxic. We don't want to use any harmful solvents in our resin. Some resins from other manufacturers, they smell awful. I compare them to smelling like gasoline or even paint, like aerosol paint, because they smell so bad. So we try to make sure that our formulas have low odor. We want to make sure that our prints have great adhesion to the build plate. There's nothing more frustrating than printing an object and then coming back to it and then finding that it did not stick to the build plate. And then, of course, easy post-processing. How are we going to clean the objects that was printed? Do we need to use an alcohol bath? Can we use water? And then from there, how do we do our final cure? So these are all key points that we look for when manufacturing resin after we have developed a formula. So we have to do all these different prints and all these different tests, and it takes hundreds of hours to actually qualify it. And this is what makes our resin so great, is that we spend time looking at our resin. We do tons of prints just to make sure that it's at a quality that we find suitable. And this is just for any resin that we do. Beyond that, how do we qualify medical devices? What about resins or formulas for a medical device? Well, here in the States, we have a Class 1 medical device and a Class 2 medical device, and this is through the FDA. So a Class 1 medical device is short-term contact into the patient. So an example of this would be a surgical guide, a try-in denture, indirect bonding tray, impression tray resins. So all of these, we have to go through and do tests for biocompatibility. So we have to do a cytotoxicity test, we have to do a skin irritation test, and we have to do a sensitization test. Now, all of these tests, these are not performed here at webmix. We have to send those out to a third-party vendor. So this is what makes some of the biocompatible resins so expensive, because we have to go through some of these expensive tests to make sure that it's not going to be harmful for our patient or for the user laboratory. Now, a Class 1 medical device does not require FDA approval. It does not require the 510K. However, the medical device Class 2, this is long-term contact into the patient. Examples of this would be like a denture base, denture teeth, temporaries. This requires extensive biocompatibility tests, 10+ tests for making sure that's not going to be harmful to the customer or to the patient. And the FDA approval of a 510K is mandatory for a Class 2 medical device. Now, this is easily confused with some of our competitors' resin that state that they have a Class 2A biocompatible resin. Class 2A is not in the United States. That is not FDA. That is through that's a European standard. Now, that may state that it is non-toxic. It is biocompatible. A human in the United States is no different than a human over in Europe. So why wouldn't it not be harmful to us if it's not harmful to them in Europe? I get that statement a lot. But for legal reasons, I would make sure whatever resins that you're using, if it's a biocompatible resin, do your research and see if it needs to be a 510K approved resin. And then also, let's go into a little bit more of a definition. So formulas for medical devices. Resin formulas for medical devices need to meet the following criteria. So they need to meet an international standard for mechanical properties. So an example of this for dentures and night guards is the ISO 20795-1 and 20795-2. An average expense for webmix to do these tests to make sure that we meet these mechanical properties, it's about $20,000 to $30,000. And then beyond that, if we want to meet the international standard for biocompatibility, ISO 10993. So this includes tests for cytotoxicity, skin irritation, sensitization, genotoxicity, and there's a couple more that I didn't list just because I didn't have room. But if you look up the ISO 10993, it'll list all the tests that we have to perform. It's $100,000 plus 5 months of testing on an outsourced third-party laboratory. So you can see it takes a lot of time just to even make sure that we have a medical device that's biocompatible, and it's extremely expensive. And this expense gets handed down through the resin and obviously in our sales. But the Class 2 medical device requires a 510K, which is a pre-market submission made to the FDA to demonstrate that the device to be marketed is at least as safe and effective to an already marketed device that is not subject to pre-market approval. So for a great example of this is creating a 3D printed denture. The denture-based material has to have a prerequisite, a pre-market approval. So there's already an object that is approved by the FDA, a denture base, and so we have to demonstrate that the printable denture-based material is at least safe and effective as an already material that is registered with the FDA. That is a denture-based material that is non-3D printed. So we can see that there's months of tests that have to go into that, and it's fairly expensive as well to go through that. So we just seen how we qualify our resin, the amount of tests that we go through, what we have to go through for a medical device. But what about after that? So before we can even start selling a resin to the public, we're going to go through testing internally in our practical laboratory here at webmix. So this is going to be a minimum of 20 hours of printing by our technicians here. So for example, me and a couple of my other colleagues, we'll go through and we'll print this resin. And really what we're looking for and defining is the design parameters for that resin. So for example, we'll find the requirements for 3-shape exocad and dental wings for models with removable dies, or if we need to find a minimum thickness for a castable resin, or if we need to find offset parameters for a splint resin, offset to the device to the teeth, or even for a surgical guide, the guide to sleeve offset. So there's tons of parameters that we have to be able to validate and verify before we can even offer it to our customers. We want to make sure that when the customers get our resin, they're having success right off the bat. And then after we do our practical lab testing, it's going to go into a customer beta testing. So 2 to 3 weeks of customer prints. Customers going to test the resin and provide us feedback. Some of the most popular topics is, what did you think of the overall resin, the quality of it, the color of it, the surface quality? How did it work for your device? How did it fit? Did we have issues with fit? And then any glaring issues that the customer had or suggestions on it. And so let's say if we released a resin, that customer did not like it, none of the customers liked it, we're going to take their feedback, and guess what? We're going to start all the way back in the beginning, and it's going to be 200 plus hours of testing. So it's a vicious cycle, but we want to make sure that we produce a high quality resin for our customers and for 3D printers. So when you start printing and start using the resin, of course there are some health hazards. So skin contact, there's irritation leading to rash. Extended exposure may cause allergic reactions and dermatitis. So I just want to cover some of the safety protocols. Eye contact, irritation leading to excessive tearing or itchiness or even blindness. Some of the resins, they can have a high toxicity with fumes, so you can lead to coughing or headache, breathing issues, and nausea. And of course, ingestion, irritation in the stomach may cause nausea and vomiting. So when we develop our resins, we're going to look at these health hazards. We're going to place on the bottles, if there are any health hazards, what they potentially could be. And of course, you don't want to just use this as like lotion, rub it on your skin. You don't want to put it in your eyes. You don't want to inhale it. You don't want to ingest any of these resins because they are toxic. But we try to reduce the effect that it has on the patient itself or on the end user of the resin. So how do we handle resin itself? We're going to use we want to make sure that we're wearing an apron or a lab coat, vinyl nitrile gloves, safety glasses, and a mask depending on if it has a high amount of fumes to it. And then, of course, the ideal print environment. Make sure that you keep your workspace clean when handling these resins, well ventilated, and then if possible, if you have an emergency eye wash station. It is possible that some resins, if the viscosity is very low, they can splash easily. And if you get that in your eye, you definitely want to make sure that you wash that out. So I just want to cover real quick what resins webmix offers and all the resins that meet those requirements, those qualifications that we go through and all that testing. So currently we have a varimodel resin. So this is for use in creating all dental models, so orthodontic models, implant models, study models, crown and bridge models, denture models, RPD models. They offer sharp occlusal detail, and we're available in the following colors. We have ivory, golden brown, violet, and orthodontic white. Violet and ortho white, those both resins can be used with 405 nanometer printers. So if you have a 405 nanometer spectrum printer for DLP, you can and should be able to use those resins in your printers, but you will have to maybe do some potential footwork on your end to make sure you have the proper exposure times. We offer a VariGuide resin, so a surgical guide resin. It's for creating surgical guides and position guides. It is a class 1 medical device. It can be polished or lacquered for a crystal clear appearance, and this stuff is clear, and this is to be used in the 385 nanometer printers. We have our Varicast resin for creating castables or pressables, full contour crowns and bridges, copings, bridge frameworks, RPD frameworks. Offers great detail and is extremely smooth when it comes out of the printer. And this is at the 385 nanometer spectrum. So I get this question a lot. Can this resin be used in a 405 printer? The answer would be no. It is meant for the 385 nanometer spectrum. And of course we have our VeriTray for custom impression trays. That is available in a neon green color, and it is 385 nanometer spectrum resin. So it does have to be printed in a 385 nanometer printer. So coming soon to a printer near you, I actually spoke with our photopolymerist and spoke with her about what resins do we have in the future, what's coming down the pipeline here at webmix. So currently we're working on a flexible gingiva mask resin for implant models. We have denture base coming down the pipeline, and denture teeth with a 510K. We have denture try-in material. We have splint resin with a 510K, hopefully coming soon. We also have a new surgical guide resin that's going to work for 385 and 405 nanometers both. We have a varimodel gray resin, which is going to be for 385 and 405 nanometer resin. So they'll be able to work for 385 and 405 printers both. And same with our Varicast that will be coming out here in the near future. It's going to be able to work with both spectrums, 385 and 405 nanometers. So here in the future, if you have a 405 printer, please come to us when we start to release new resins to see if it would be compatible with your printer. And thank you for joining us. If anybody has any questions, this actually completes our webinar. Let's see here. Don't see any questions as of yet.
Done a great job. No questions. Well, while we're waiting for any straggler questions, I just want to, first of all, thank Cory very much for doing a great webinar as usual. And secondly, I want to remind you that if you are a CDT, you will get credit for the program. It'll take about a day or two, and you'll receive an email that will explain how you'll get the credit. And then the other thing is that it is a recorded webinar, so within 24 to 48 hours, you'll be able to check the webmix.com website and go to the webinar section, and you'll see this very webinar up, and it'll stay there for a very long time. Well, we don't have any questions. I guess that's a good thing. I hope you all enjoyed it, and thanks for joining us at another webmix webinar. We have them every other Tuesday. I look forward to hearing from you or seeing you at a future webinar. Thank you. Bye-bye.